Hello everyone. So today we are going to solve the problem symmetric tree. So given the root of a binary tree, check whether it is a mirror of itself, that is symmetric around its center. Okay. If you see the example, this is the center. Now let's check for its symmetry. This 2 and 2 are same, this 3 and 3 are same, and this 4 and 4 are same. These two sides are totally mirror of itself, right? So this is a symmetric tree. Now what about this? If we draw a mirror around its center, we see that this and this are mirrors, but this and this are not. Why? We can clearly see, right? In order to make it a mirror, this tree should have been here, somewhere here, right? So this is not a symmetric tree. Okay, since it's a tree, okay, we have to check its symmetry, right? We have to check all the nodes, isn't it? So we definitely have to do some traversal, right? So we are going to look at both our BFS and DFS traversal approaches, how we can use them to solve this problem. Okay, so let's talk about our BFS approach. Okay, so what is BFS exactly? It checks level by level, right? So when it checks level by level, let's talk about levels. Okay, let's see the first level. It's 1. Does it look like symmetric? Yes, it is. It's just a single node. Now let's see the second level. It's 2 and 2. Does it look symmetric? Yes, definitely. Now let's check the third level, that is 3, 4, 4 and 3. Does it look symmetric? Yes, it looks symmetric around the center, right? What is it exactly? It just looks like a palindrome, right? Now let's talk about this tree. The first level is 1. Is it symmetric? Yes, it is symmetric. What is the second level? 2 and 2. Is it symmetric? Yes, it is symmetric. Now what about the third level? The third level is something like here there is a null and there is a null. Okay. So null 3, null and 3. Is it symmetric? No, it's not symmetric. How would it look like if it were symmetric? It would look something like, let's say 3 null and null 3. Let's say this 3 were here and this null were here. Okay, or let's say this 3 were here or this null were here. Okay, in that case it would be symmetric. So the approach is pretty clear. Now we are going to do a BFS traversal, okay, and record our level in some data structure. Okay, and we are going to check if that level is symmetric or not. Symmetric, how? We will check if it is a mirror around its center or if it is a palindrome. Okay, so that's what our approach is. So this is the solution. We use a queue, we insert the root node, and we normally do our BFS like we do. But here we initialize a array list, okay, called level. Okay, this will record the current level because we have to check if the level is symmetric or not, if the level is a palindrome or not, right? So we pull the current node from our queue, and if the node is null, okay, if the node is null, we add the null value. Okay, because in the example we saw that the level was something like null 3, null and 3. So if we ignore this null, it won't work, right? We have to add it, isn't it? So we add that null. Otherwise, if it's not a null, let's say the tree was something like 1, 2, 2, null 3, null 3, right? So if it's not a null, we add this to our list as well as add both the children. We have to add both the children, isn't it? We have to add everything in that particular level, isn't it? So we add the value, we add the left, and we add the right. Add the current node's value to the list and add the children to the queue, isn't it? Because when we will come to the next level, these nodes will be pulled out, right? So after we have recorded our level, we will see if the level is symmetric or not. Okay, for that we have a separate method, is symmetric level. Okay, so this is the method to check the symmetricity of our level. Okay, this is simple, this doesn't need an explanation. Okay, we can do it using a while loop as well, while I less than j, I plus plus and j minus minus, right? Just how to check for a palindrome, right? So is if our level is not symmetric, then return a false, otherwise we will continue our iteration. Okay, now what is the time complexity? The time complexity is of course a big O of n, right, to traverse the tree. Now in each step we are checking this asymmetric function, right, that is traversing the level. Now what can be the max size of a level? The max size of a level can be n by 2 plus 1, that is the width, max width of a binary tree, the bottommost, right? So that is given by n by 2 plus 1. Now if we do a n into n by 2 plus 1, okay, we will have something in quadratic, right? So ultimately our time complexity is going to be quadratic. Okay, we go of n square. because at each iteration we are checking this, we are iterating over the whole level, right, which can be at max n by 2 plus 1, right, which is ultimately linear. Okay, so this is the time complexity. And what about the space? The space complexity is a big O of n for the q, right, and a big O of this, which is nothing but linear at the end. Okay, so space complexity is big O of n. Now let us talk about our DFS approach. Okay, now what do we do in DFS? We go to the depth, right? Okay, we go to the depth, we come back, then we go to the other side and go to the depth, right? Now in this situation we have to see that when we come to this side, if this node, the node value is equal to this node value as well, right, we have to check this. But since our DFS works in one side at first, then the other side after coming back, then how are we going to compare these two, right? So we have to do something like that. What we will do, we will move down at both sides simultaneously. Okay, so from root we will come to the left, we are here, then we will also at the same time we will go to the right as well. Okay, now we will see if these two nodes are same or not, if the node values are same or not. Okay, they are same. Now what to do? We have to go down, below, right? So we will ask our DFS to go down. So this side, we will go to this side. Okay, now as our DFS generally works, we go to the left side, then we go to the right side, isn't it? But here the thing is different. We have to compare this node to the node at the other side, which is at the extreme right, isn't it? This one is the extreme left, this one is the extreme right, isn't it? This one is in the inside, this one is in the inside. So if our DFS is running in a normal fashion in this side, then our DFS has to work in a reverse fashion in this side, isn't it? Because if it's going to the left, then it has to go to the right, isn't it, to compare this and this. If we tell our DFS that okay, in both the sides go to the same side, here go to the left, here also go to the left, then we won't be able to figure out if it's a symmetric, right? That's what a mirror is. If our tree is a mirror, okay, if our tree is a symmetric, then our DFS has to move in a symmetric fashion as well, right? So we'll ask our DFS, okay, in this side go to the left, but in this side go to the right, okay, and compare if they are same or not. Yes, they are same. Okay, they are same. Now we will return a true from here, isn't it, that okay, they are same. Now we will tell our DFS, okay, now check the other subtree, now check the other side. So in this side, now we go to the right, then in this side we go to the left. So how is the thing happening? We are here and here, we ask this to go to the left and ask this to go to the right. Okay, now after they are done, they come back. Now we ask them to go to this one to go to the right and this one to go to the left. So how is the thing happening? If this is our left and this is our right, so left and right, first we are asking this left to go to your left, okay, and we are asking the right to go to your right. Then we are asking our left to go to our right, and we are asking the right to go to its left. Okay, isn't it? So left left, right right, then what's happening? Left right, right left, isn't it? This is the fashion of our movement, of our traversal. Okay, let's see this one. We start from here, we come here. This is our left and this is our right. Okay, we ask, hey, left and right, are you both equal? Yes, we are equal. Okay, left, you go to your left, and right, you go to your right. Okay, now we see that left has come to a null. Okay, and what about right? Right is at 3. We compare, hey, left and right, are you guys equal? No, we are not equal. One of them is null, one of them is an integer value 3. So our tree is not symmetric, right? Now assume these two were equal, right? So this would have returned a true, this would return a true. Now we will ask left, okay, left, you checked your left, now left, you check your right as well. And we will tell right, okay, right, you checked your right, now check your left. We'll check their left. Now if they are same, we have a symmetric tree, they will return a true, otherwise they will return a false. Okay, so the thing is, if we are doing a normal traversal at one side, okay, we are doing just the opposite at the other side. Something like this, you can say. We are going to the left, but in this side we are going to the right. Just the mirror, we are doing the mirror work at both the sides, isn't it? We go to the right, we come to the left. Just the mirror. We can see the traversal is also happening in a mirror like fashion, isn't it? Inverted fashion. This is how we will check for the symmetricity. Okay, here is the code. From our root node, we send our DFS to the left and right. Okay, this and this, let's say. Then they will check if they are null. No, they are not null. If are they unequal? No, they are not equal. So they will go down. Left left, left's left, and right's right. Okay, Let's assume they return a true. They returned a true. Okay. Then we will say, okay, left, you go to your right now. Left, go to your right, and right, you go to your left. Okay. Let's say they return a true as well. So this is check 1. Let's say check 1. It returned a true, right? This and this returned a true, and this one also returned a true. Okay. So ultimately, we will return a true. That okay, we have returned a true from down below. Okay. Now let's say at any instant, let's say a value at one place is something, but in the other place it's different. So this condition will be triggered and we will return a false, that no, our tree is not symmetric. Or let's say one node is null. Let's say this one is null. This one is null. Then this one also has to be a null, isn't it? So if our left is null, return if right is null or not. Okay. If it's a null, it will return a true. If it's not a null, it will return a false. Now let's say if our right is null, okay, we will see that okay, is left null or not. If right is null, left also has to be null. So if it's not a null, it will return a false, otherwise it will return a true. Okay, so these are our base conditions. We can simplify this part, okay, a little bit. Let me show you how. So instead of checking for both left and right, we are checking left and right in just one condition. Okay, either if left is null, then it would be a true. Okay, so we will check if left is equal to right, if right is equal to left. Let's say left is null, then it will give a true. Then we will directly enter here. Then in that case, our right also has to be null, right? Left and right has to be equal. So if they are not equal, it will return a false, otherwise it will return a true. Similarly, if our right is null, we will check is our left equal to right or not. Okay, so if it's equal, then it will return a true, otherwise it will return a false. It's just a bit concise than the previous way that we did. Okay, so this is the solution. Now what is the time complexity? Time complexity is a big O of n, right? We are performing a DFS, and our space complexity is a big O of n. Okay, the recursive stack space. So I hope you guys understood both the approaches, right? BFS and DFS. In case you have any doubt, you can ask anything in the comment section. Okay, so yeah, that's all from my side. If you like this video, do hit the like button, share this video and subscribe to my channel, and I will see you in the next one. Bye bye.